Alrighty, here we go. Lesson 6-2, part 2. So we just found the perpendicular bisectors of every side, and we found that the perpendicular bisectors meet at a point of concurrency called the circumcenter. What we're going to do right now is do the angle bisectors. So in the perpendicular bisectors, remember we looked at an acute triangle, a right triangle, and we looked at an obtuse triangle. And the point of concurrency for an acute triangle was always inside the triangle. If it was a right triangle, that point of concurrency is at the midpoint of the hypotenuse. And for an obtuse triangle, that point of concurrency, the circumcenter, is outside the triangle. Okay, so here for angle bisectors, we're going to do the same thing. If you have an acute triangle, where is the point of concurrency? If you have an obtuse triangle, where is the point of concurrency? And if you have a right triangle, where is the point of concurrency? Okay, so here we have an acute. So if we do angle bisector, angle bisector, angle bisector, okay, they meet at a point of concurrency inside the triangle. Now, what happens here is my very bad drawing here shows that the distance to each side is going to be the same. So let's use a better example. So in this next screen here, I have an obtuse triangle. So if we have the angle bisector, and angle bisector, okay, obtuse triangle, we found out that it is also on the inside of the triangle. Okay, now what happens is you see this circle here is if we go from this center, this point of concurrency, and we go to each side perpendicular to the side, perpendicular to the side, perpendicular, these blue segments are all the same. Okay, so this is actually called the in-center. So the in-center is made from angle bisectors. And what's special about it is that when they are equidistant to each side. The in-center is equidistant to each side. Equidistant to each side. And this time, when you do your point and you connect, this time the circle's inside. When we did the perpendicular bisectors, remember that circle went outside the triangle, and those were equidistant to the vertices. So when we did the perpendicular bisectors, they were equidistant to the vertices. Now look at this. From here to the vertex and here to the vertex, those are not even close to being the same. Okay, so we just found out in an obtuse triangle, it is also inside. Okay, and that also happens for the right triangle. So we could certainly do another one, but if you do inside, the point of concurrency is always going to be inside for your angle bisectors. All right, so let's see what special things we have. In-center. The in-center. So this is a screen you're going to want to pause, stop, and write down all this information. The in-center is made from angle bisectors. And they are always inside, whether you have an acute, obtuse, or right triangle. That point of concurrency, the in-center, is always inside. And then the special thing that happens here is that this incenter is equidistant to each side. So PY, PX, PZ are all the same length. Okay, so if we look in here, something even more, BY is congruent to BZ because this is on an angle bisector here, and because it comes down perpendicular, that this segment is congruent to that segment. Okay, the same thing happens over here. So if we look at this one right here and look at this green triangle, okay, CZ is going to be congruent to CX. Now, CX does not equal XA. Those are not the same, but so AX does not equal XC. If it did, then those would be bisectors, and it's not. Oh, wait a minute. In one kind of triangle, AX would be equal to XC. What kind of triangle would we have? Yep, it'd be equilateral. So an equilateral triangle, the angle bisectors and the perpendicular bisectors are the same thing. All right, let's see what we got here going on for problems. Okay, so get this copied down, and when you have it copied down, then make sure you go ahead and try and solve this, and then resume your video so you can check your answer. All right, in the figure shown, QM, so let's find QM, and QN, let's see, they give us those two. Let's see. This red mark QL is an angle bisector because we have this double mark and this double mark. And QK is an angle bisector. So this point right here, Q is the in-center. If Q is the in-center, then that means that QN is equal to QM, and it's equal to QP, because the distance to each one of those is going to be the same. So now they're saying QM is 3x plus 8, and they tell us QN is 7x plus 2. They must be equal because they go from the in-center to the side, the length to the side, so they have to be equal. So I'm going to subtract 3x, and I'm going to subtract 2. These cancel. 8 minus 2 is 6. Is 7x minus 3x is 4x. So now I am going to divide each side by 4. Looks like I'm going to get 3 over 2, or 1.5 for x. All right, now they really want to know what QP is, so it doesn't matter which one I plug this into. So I'm just going to take 3 times 1.5 plus 8. So grab your calculator. 3 times 1.5 plus 8. And I got 12.5 here. All right, so if you would have plugged it into the other one, you should get the same thing. 7 times 1.5 plus 2. And I believe if I did my math right, that comes out to be 12.5. So it doesn't matter which one you plug that into. Okay, so recap, this was the in-center. In-center is made from angle bisectors, and they are, the in-center is equidistant to each side. Earlier lesson, circumcenter is equidistant to each vertex. All right, you should be all set and ready for all of your Chapter 2 homework. Good luck.